Yes.
All right, so what's here? There, up down on this side. Big man on this side. Now I'm here down there. That's two. I'm figuring it open here. Right? So what's there, right? Last day we focused on the ideal gas equation, and we saw that PV and T are related by this equation. This one based on number of moles, this based on number of particles, and this based on finding the average speed of all the particles. Then we were able to show a relationship between kinetic energy and temperature, right? So we said that the kinetic energy of an ideal gas is equal to 300 kT, right? This is the average, right? Today, we're going on to something called thermodynamics. Right? And we're going to take a look at the first law. Real simple concept, right? So let's say we had a gas trapped in here, right? And I would like to know the things that change the internal energy. Right? Things that cause the internal energy change. Any ideas? Internal energy change and delta U. What are some of the things I could do to change the internal energy? What's internal energy again? Find ideal gas. Find ideal gas internal energy is equal to what? The energy inside the gas, right? Internal energy. So the energy inside the ideal gas is purely what? Purely what? Kinetic. Purely kinetic. Right? So I would like to know two things that can increase this here atom. Right? What are two things, Adam, that could probably increase the internal energy inside that gas? Okay, how? How can put pressure on it? Hotter? Right, heat. So I can apply heat. Right? That's Q. The symbol I use for heat is Q. Right? That's heat energy. In this case, positive, so it's applied. What else I can do? What else can I do to increase the energy inside it? Compress it. Right? Compress it means I can do work on the gas. Right? So I can do work on gas. Sorry. Right? I can do work on the gas, on the gas. Sorry. So I could compress the gas. That's okay? So if I add energy and if I compress the gas, do work on the gas, right? I would be able to increase the internal energy in this. So this here is what we call the first law of thermodynamics. Everybody okay with that? Right? What would happen if work? What would happen if huh? What would happen if work was done right like that? What would happen if you have work done by the gas? Suppose the gas is doing work. What would that do? Suppose the gas doing work instead of you doing work on the gas. Suppose the gas was doing work. What would happen? It would expand. Would the internal energy go up or down? Down. Right? If the gas expands, then the internal energy becomes smaller. Okay? So if work done by the gas, then it becomes what is it becomes delta U is equal to Q minus W. Right? Why minus? Because work is now being done by the gas to make the internal energy smaller. Everyone, you okay with that? You sure? Right? I know I'm making it right, but everything here is in your hand, okay? Yeah. I don't put it somehow or something. All right. So this is the concept of thermodynamics. Whenever W positive in this version, right, is called work done on the gas. Whenever W negative is work done by. Some versions have it a little bit different. Some books you might see Q as the subject. Q is delta U minus W, right? So you might see different versions. I like this one because it's easier for you to understand that these two things increase internal energy. The other way around. Make Q the subject and the formula. Why not use it? Theta. No, Q is energy, like easy. I get it. Theta. Yeah, use it. Oh. But E is equal to that is the actually right? But I'm going to come to that later. Popeye's. Ready? All right. Yeah. Right. So something that we said earlier, we said it right here. We said that internal energy is purely kinetic. That's okay. But I want a little wait, yeah, okay. So that's so yeah, yeah, I want a little help. Anybody can help me get a relationship for kinetic energy? I'm just like for internal energy based on the list I gave you. 300 kT, right? So U is equal to 302 kT. All right? U is equal to 302 kT. Right? So let's make sure you remember that, right? Right? And the reason we have this is because kinetic energy is dependent on temperature. So it means that U will be dependent on this as well. K is what again? Where's K, Adam? K is what? What's this K here? Or this K? Oh. Right. Boltzmann constant. Pardon? Because K is constant. K is Boltzmann constant. R is molar gas constant, right? Mean square. Is in the notes on that? Yes. Oh, you remember. All right, nice. So nice. So let's get involved in some other things, right? This energy here, this energy Q, we'll look at it in a little while, right? But what's important is what is work done. So you want to focus a little bit on what is work done. I have a little chart I want to go through in the notes just now, right? But work done. Work done. Anybody remembers how to find work done? Power by time. What else? No, easier. Power work. Sorry, work done is only what? Force by distance move, right? Force by distance move. And force is what? Force is pressure by area. Force is pressure. Remember, we're dealing with these quantities here, right? Pressure, sorry, work done is equal to force by area. Sorry, force is pressure by area. What is area by depth or by change? volume, right? So for example, let's look at this little piston here, right? If I apply a force here and there's a little change in distance, then work done is equal to pressure by change in volume, right? Work done is pressure by change in volume. Huh? Right, copy it up. Right, so what we're seeing there, we're seeing that work done is equal to pressure by change in volume. Right, so pressure and volume inside here controls work done. Right, otherwise think about current and thing, right? I want you to only think about pressure, volume, temperature. Those are the three quantities that we're focusing on. How pressure, volume, and temperature controls all these things here. Right, while you're writing, what would happen if a gas, if you have gas and pressure, but no work, sorry, there is no change in volume. Suppose you're applying a force here on the piston, but there is no change in volume. How much work is that? None. Right? So if you're applying a force here and this not changing, right? Although there's pressure in here, no work done. Right? So if change in volume is 0, then the work done will be 0. All right. So those are the things I wanted to understand about the first law of thermodynamics, right? Let's take a look at the notes there. Okay. Paul, if anyone, what's last one? Yeah. Was it? And I wear it. I feel like we're mugged again, no? No. Well, they actually didn't know they want to. But they had tension and two chickens. Somebody had their switch to. The lady what? Two shrimp for their switch to. That's the ones down by food basket. Right. So there's something I want to point out here. Here, we look at the notes. The law is delta U is equal to Q minus W. Right, we talk about that. It's only a minus when work is done by the gas. Right? If the gas doing work, it's going to lose internal energy. Right? That's why it decreases, right? But below here, there's a table I want to go through. I want to make sure you understand the table, right? If in your notes, say you don't have to write. Right? Look at the top there. Delta U is the change in internal energy. So we're looking at the first row, right? First column, right? Focus on delta U alone. If the temperature increases, then delta U positive. That makes sense? If the temperature increases, delta U positive. That makes sense? Dante? That makes sense? Right? If you increase the temperature in a gas, the internal energy should go up. So now you do it up. What about if it drop temperature? The internal energy will drop. What would happen if there's no temperature change? Then there is no change in internal energy. All right? So there must be a change in internal energy for you to end up, sorry, a change in temperature for you to end up with a change in internal energy. Everybody okay with that? Joseph? You okay with that? Next one. I'm on. Right? Q is heat energy. Right? If heat enters the gas, then obviously Q will be positive. Right? If heat exits the gas, then Q is negative. Everybody okay with that? And lastly, if there is no exchange of heat, then Q will be 0. Right? Simple enough, right? Yeah. Last one, work done. If it compressed, work done on the gas is positive. That makes sense? On, right? If it expands, work done on the gas is negative, right? And if it's constant, then the work done is 0. Everybody okay with that? I have a small question. What would happen if it's work done inside the gas? If it's by and it compress, W is what? Negative, right? If it expands, W is, and well, if there's no change, it will be. Everybody okay with that? So those are the concepts that I want to understand about each one, right? Each one of those is a different type of process, right? So here we have different types of processes. We have an adiabatic, isothermal, isobaric. So if you look here, I don't have values, I'll give you values just now, right? Isobaric is a horizontal line. What type of graph is that? What type of graph is that? Pressure versus volume. It's a pressure versus volume graph. So isobaric is this horizontal line here. What do you think isobaric means? It's a horizontal line on a pressure versus volume graph. What do you think isobaric means? Pressure. Excellent. Pressure constant. Very good, audio. Pressure constant. Right? So isobaric means pressure constant. What does isothermal mean? Constant temperature. Right? So it means that between here and here, or wherever, temperature remains the same. And adiabatic, well, you wouldn't know this one, but adiabatic means that everything changes. Pressure changing and volume changing. Okay? Right? So add that in at least an isobaric process. No, normally I'll give it up for homework, but starting in full series. Isobaric process. Anyone? Just keeping temperature constant along the curve. Remember, this graph will only show pressure and volume. So if temperature constant, it could be anyone. You just have to highlight temperature staying the same. Right? Isobaric means constant. Isobaric means constant pressure. Isothermal means constant temperature. Isothermal means constant temperature. Isochoric, not it. Look at here, right? Isochoric means constant volume. This one here. How would I show it on the graph? How would I show isochoric on the graph? A vertical line, very good. A vertical line. Nice job. What's the work done during isochoric? What's the work done here? LV0, right? So if I draw a horizontal, a vertical line, right, the work done is 0. And last one, adiabatic. What are you doing then? You know, adiabatic is constant. Adiabatic is varying pressure and volume. With no heat exchange. With no heat exchange. Right? Adiabatic is varying pressure and volume with no heat exchange, which means that Q is 0. Which means that Q is 0. Keshav, if based on this law here, right? If Q is 0, what you can say about the internal energy? If Q is 0, what you can say about the internal energy? Right away. Q is 0, right? So all of the internal energy comes from the work done on the gas. That's okay? Right? So all the work you do on the gas, that goes purely towards the internal energy. All right? So you would see in calculations, you might say, hey, there's that adiabatic process. Find something. Right? Q is 0 and then it is solved. Right? Before we start any question, I want to do one thing with you before we start, right? Oh, I didn't ask you. I forgot to ask you, right? Watch here. If I give you a pressure versus volume graph, Connor, if I give you a pressure versus volume graph, the area under the graph is the work done. Right? That is why when we had the vertical line, you all told me that the work done is 0. Right? Because the area on that line is nothing, right? That's okay? So if I give you a pressure versus volume graph, the area under the line is the work done. All right, just jot it down now. Work done is, you know what, enjoy. Work done is equal to area under the graph. Right, I want to point out one thing and then we could move on, right? Adding this to our 5 formulas from last week. Sorry, four alone? Oh, the density formula, you had to write that, right? So add in delta U is equal to Q plus W. Online, if you're not seeing, press the camera, right? And I also add in W is equal to P by delta. Right? And well, squeezing this in, U is 3 on 2 KT. That mark was over. Yeah. Like 2 lines ago. But then I really feel so detailed. No, I have a much more job. What about this height? Can you run the box? Is that a height?
But it's.
Yeah, but this is what it was. Thing must put them out.
Yes.
Now,
It was 100.
at 12.
Well,
About.
12, so that one.
Number 12. That one. Oh, okay. I don't know. Sorry, bro.
$5. Yeah.
Unless I figure out. See that it moves.
I think I see almost on that.
Sometimes you do have a thinking. That's what you do. Who's the I'll take him more than 2 days. But he doesn't when he go away, he doesn't get it. I'll look for somebody. He's very small, not white. Oh, it's really. Right. Last thing I want to talk about was something somebody was pointing out, right? What happens during temperature change and thing, right? This whole thing in your notes, but I want to show you it in full on the board. And then we have practical questions. But okay, okay, so far, it makes sense? Just come with a hook question and I think it through your ear. Think your ear is this or anyway. We learn everything, we get narrowed up. Last year we get 2 out of 3.
So who's me?
I mean, like when I do the prediction, they get 2 out of 3 last year. This year we get 1.5. No, actually we get 2.5. Because sometimes the whole topic will be question. Sometimes it's better. Last year they do real good. 2.5 one of the years. They almost get the whole paper. And the all-nighter get a mock exam with the same thing. Sometimes a lot. Right. So what I was going to say now is somebody was asking, what about Q? Right? Everything has a formula. Work done have a formula. Internal energy have a formula. Right? So why not Q? Right? Whenever you apply heat to a substance, it causes a temperature change. Right? So what we're going to look now, instead of using E is equal to MC delta theta, right? I'm gonna add it in here, but you don't really use that, right? Instead of using based on mass, Adam, what we're gonna do now is we're gonna use it based on moles, right? So we're going to look at something called molar heat capacity. And to make it more complicated, what we're gonna do is that we're gonna keep volume constant and we're going to keep pressure constant, right? And we're going to observe what will happen here. That's okay? So this relationship comes from this, right? But instead of mass, we use it moles, right? So those quantities like C is what you call your molar huh? C is called your molar heat capacity. Time up, see what. Yeah, push on. Right, so C is your molar heat. Hey, boy, get the money wrong, Marcus. Anyway, we will be on makeup. Right, so let's start with Q is equal to NCV delta theta. Right? Right, so what does CV mean? CV means at constant. CV means at constant stopping P. This will be at constant pressure. And I'm putting V here. This will be at constant volume. Right. What do we learn about constant volume? We learned that constant volume work done is 0. That's okay? So let's come back to here. So at delta theta is equal to, sorry, change in volume is 0. What do we know? We know that Q will be equal to delta U. Right? Let me make a full sum. So I'm trying to save my mark. All right. So delta U is equal to Q plus W. So if I put Q in here, I will get delta U is NCV delta theta. But W is what? 0, right? Are you okay with that? W is 0. At constant pressure now, Q is equal to NCP delta theta. So what would delta U be? Delta U will be equal to Q plus W. At constant pressure, is there work done? Yes. So we're going to get delta U, which is NCV delta theta. Right? So I'm taking delta U as this now. I write in Q, which is NCP delta theta. And well, there is work done, so I'm using this here. Work done is pressure by change in volume. Almost done. 2 minutes again. Are you okay with this? Right? I run over fast. All I showed you here is that at constant volume, W is 0, so Q is equal to this. I wrote what Q is and I make it equal to this. Yeah, we're gonna prove something. Right? I'm gonna bring out something together. Real cool stuff here. Right? So delta U is this, delta U is this, and Q is this, and W is this. Right? What's going to happen now? We know that PB is equal to what? Online, all okay? Right? Last thing, and that's it. No more theory again, right? PB is equal to nRT. That's okay? So what do you think is P delta V? What would have happened if I change the volume? What will change here? N is moles, temperature will change, right? So I end up with delta T, right? So it means that P, so now I'll have something like this. Instead of writing P delta V, I write it NR by the change in temperature. That's okay? But you all recognize that everywhere here have moles and change in temperature. So you end up with CV is equal to CP plus R. That's okay? So what does it say? This says that CP minus CV minus CP is R, which also means that this is bigger than this, right? So it means that way more heat is required at constant volume than heat required at constant pressure. And when you minus them, you get R. So it shows you what R is. Oh, sorry. R is the molar gas constant. Right? So again, this is if we use work done on the gas. I think I gave you a version in there, work done by the gas. Right? Theta is temperature change. Theta is temperature change. So When we change the volume, temperature will change at constant pressure. That's okay. You don't have to write down in the notes, right? I just want to write down the relationship here. Right? The one in the notes is right. So let's just change that, right? The one in the notes is right. So you just change the sign. Work done by the gas, right? So let's use the one in the notes with the minus sign. Take us 2 minutes, look over everything that we did. We're going to try some questions, right?
Say minus go. Nice. Remember, best round turn you want to. Really. No. But he trucks off, he trucks off, trucks off, I wouldn't mind it. There's not only it's all trucks.
Yeah, I'll see you last second. Yeah, by something I don't know what it is.
So it's not good every day.
Yeah, it's kind of root there.
Good every day.
I want to wrap it out too.
It's not too big.
Like change the sign over there. In the proof I use work done part, right?
Yeah, but anyone's struggling.
I was messaging you. But when I was listening, I was right there.
But that was you.
Yeah.
Say hi, I was right yesterday.
It was quite up the street, I was messaging you. Oh, I was when I see it, I was like,
See what I'm doing.
yeah, she's not big enough. That's not familiar. Right, so make sure you remember what each one is, right? What each variable here is. Right, let's see if we could put this together, right? Yeah.
Here I'm the thing something else.
So far afternoon.
Everyone fine.
All right, so let's start with a small example here. Are you ready? You ready? Everybody ready? Let's take a look at this now. Take a little read. Right? Take a little read there and let us let's try that, right? Just do my paper now. Just take a roll it. And I'm gonna 5 weeks. Five people. Yeah, I got one. Wait, names coming out. Wait, name one time. Right, so let's go. So temperature, what they give you there? What did they give you there? What year? I don't know what year. Right, moles, they gave it N. Right, they gave you temperature change, so you can work out delta theta if you have to. And they gave it pressure, constant pressure. Look at the bottom. What is that at the bottom corner? What is that at the bottom there? Which is what? What letter? C what? CP. Very good. CP. Molar heat capacity at constant pressure. Right? So that's CP. By the way, can we find CP? If we have CP, can we how? Yeah. CP minus CP is R. Right? R is the molar 8.31. Right? Yeah. Constant 8.31. They want you to find the thermal energy supplied to the gas, right? What do you think is the formula that we're going to use here? Thermal energy is what letter? Q, very good. So we're using Q is equal to what? Right, and Cp delta T. Excellent. Work done. Sorry. Change in volume. How are we doing that? How we getting delta V? What we going to use? Positive equation. But very good. No, they actually work done later on. Okay, but what is the W then? What else we can do? Delta V. And so you want to get which one? No, like delta V one. Change in volume. How about pressure by change in volume and our change in temperature? One on top. Right? PVs and RT. Right? If you use PVs and RT and take it find both volumes. Dante? Dante help me the next one. Part 3. Work done. What are you using to get work done? Which is P by delta. Alright, so I'll give you a little help there. start working it out and let's see what you get for A, B, and C. Right, look at what happened in part C, yeah? When you all reach there. What happened in part C? No, same change in temperature. Constant volume. So what do you need now? Right, so you need C what? So you need CV. So you need CV, right? Hey, who have you listening? Ishab man, you gotta go way past it. Not just putting it. Right, now we start to whatever start. Who was that? Joshua. Emma. That's right, Joshua. Right? That's right, Joshua. Online audio okay? right? So I have 3 by 29 by the change in temperature is 50, right? What you all got for Q? First one. 43503. Change in volume. Change in volume. I am using nRT all over pressure. So that's 3 by 8.31 by 50 all over 5 by 10 to the 5.
This is one.
Huh? For that part, no? Remember, it's changing volume that we need. How much you got, Adam? Adam, you get it?
2.493 by 10 to the power by
And then I told you how to find work done, right? Work done is pressure by change in volume. Right? So the pressure was 5 by 10 to the 5, and the volume is 2.94 by 10 to the minus 3. I got 12,045. Check out what delta V. 0.493. Why write 94? Maybe I write it wrong. Yeah. Sorry, 2.49. Right, so the work done by the gas is 1245. So now they keep the gas constant. Anybody can tell me what to do there? What do I do there? Yeah, any ideas? Susan, anything? Nothing? So remember they said what constant now? The volume constant, right? So if your volume constant, work done is 0, how that gonna help you find internal energy?
So then I find CV.
Right, exactly. So if you want to find internal energy, we saw, right, we saw internal energy is this. You okay with that? So if internal energy is this, I want you to find CV. And we know CP already. Right? There are 2 ways we can do it, and we're going to do both ways. So find CV first. Following? Find CV and then find internal energy.
Delta
U is internal energy.
Oh yeah.
Right? There are 2 ways for you to work it out. Try it now, please. Try it the same. No, delta U. Delta U is the final one. Oh yeah. I want you to use two methods, huh?
Plus US.
Huh?
And plus US.
Yeah, that's 0. Try it. Two methods.
I think it was to go. Trust it. Sorry. No, trust it. Yeah. Nine, something like this one. I say, that is just using yeah, someone's looking at it. Yeah, I don't know. That's very fair. I like to show you. No, I got that. So you talk to people. I get it. I'm a people. Was aber klar, aber der Trick ist, sie gehen Spaß, so ich würde sagen, für den Tag raus nie. Ja. Und den Blick. Das sollte ja nicht zu schnell sein. Nein. No, so when we have some kids, that's able. That's the Ja, was immer muss so ist da ja das so chance. Da eu vou fazer um café para vai tudo. They have a pretty good international relation. Yeah. Oh, what we did.
Right? All again?
Yeah.
So I want to show you. Everybody put a name here, right? Huh? Mine? Right, so what is here? Right, there are two ways they can do it. Number one, you'll found CB. Right, so CB is equal to CP minus R.
That's 20.69.
So that was what, 29,
20.6.
8.31, and I got 20 right? That's also the answer for part 2. And then delta U is equal to NCB delta theta. NH3 CB is 20.69 and delta theta is 50. How much is that? When I multiply, how much you all got?
3,102.5.
How much are they got? Right. But what's the next way? What's the next way that we can do this? Anybody saw a next way? Right? Because this question wants you to find CV after. Right? How could we have done it a different way? Look at what you have. I'm going to highlight two things here in blue. You have Q and you have work done here. Right? It was work done by the gas. What can you do? Anybody? You have work done by the gas and you have the energy being supplied. Could we have minus F? Look at this here. Look at this one down here. Could we have used delta U is equal to Q minus W? Q is 4350 minus 1245. Minus and see what you get. you'll get something very close.
So you see, no, two ones you refer.
3105. It could be a little different because of how we round, contemporary way of done. You're okay with that? So it can be done, it can be done two ways. You could use this relationship here, or you can come and use this one here. All right. Copy down. Let's squeeze in one more part. Now, that's it. We have 5 minutes. We will just talk through it.
So we have any beach.
6 minutes. We have 6 minutes.
Let's see. We'll see. I'm beach.
When you say that word?
Go ahead.
I'm going.
I never show. The piece is not the songs. I can't do something.
Right. Last thing on here. Right. Last thing. No calculation. Just theory. You get all definition for homework, right? I was saying on the group. Watch it here. Come on, watch it, Joseph. Right? A gas is compressed. A gas is compressed, and the temperature rises. Explain macroscopically using the law and microscopically. Who want to do micro? The easier one. Who want to do micro? Nathaniel, do micro for me. Alright, do micro. If you compress a gas, why is temperature going up? If you compress a gas, less space, right?
Yeah.
What I mean? Less space means that if they would collide more, and if pressure goes up, temperature will go up, right? Pressure and temperature directly related. Right. How can we explain that using macro now? Macro. Explain it using the first law that we just learned. Anybody? And we done. Nathan, you do it.
Microscopic.
No, macroscopic. Micro done. How come when you drop the volume, temperature going up? Can I do next test? So make sure you got it.
See this one that's something out there. See you grab what that says.
And Nathan, so I come up with. Add up. Sabi mana
So, where do you like macroscopic?
macroscopic means using the formula.
Oh, right. So basically, so
That's right here when we explain this.
the internal.
Right? Start with a drop in volume.
So,
If you compress the volume, what has happened? Why? No, macro. So if you compress it, right? Work is done on the gas, right?
Right.
And when work is done on the gas, the internal energy will what? An internal energy proportional to what? Temperature. Right? That's what they want. When they say macro, quantities only. Micro, particles. Let me hear it again, Adam.
So, macro, quantity.
No, I don't want to know that. I want to know the explain it. Explain why the temperature went up when it dropped the volume.
Plus, no,
Macro.
oh, yeah.
Right? When the volume drops, work is done on the gas. And if you do work done on the gas, then the internal energy will rise.
Right.
And if the internal energy rise, Keshav, what happen? Right? If the internal energy rises, temperature will rise.
Yeah.
All right? To finish your rest of work, right?
Right.
Emma,
That's
finish your rest of work.
why.